Welcome to the deep dive. Today we're taking a close look at getting shortest path bridging, or SPB, up and running in the real world.
Mm-hmm.
Our source is an expired internet draft, which, yeah, might sound a bit dated.
It does, a little.
But it's actually packed with really valuable lessons learned from actual deployments.
Yeah.
We're talking some pretty demanding setups, like the network for the Sochi Winter Olympics back in 2014.
Exactly. This isn't just theory, right? It's a distillation of hard-won experience.
Okay.
Our goal today is really to pull out the practical advice, the critical factors that made those SPB networks successful.
Right.
We want to understand the core insights without getting, too bogged down in all the technical jargon.
Yeah, cut through the noise.
And importantly, we'll focus on how to use standards-based SPB and, crucially, achieve smooth operation across different vendors' gear. Interoperability.
Right. So if you're maybe wrestling with network architecture choices or just curious about the nuts and bolts of modern networks, or even exploring ways to better connect your data centers or sites that are far apart, this deep dive should give you some solid, experience-backed guidance.
Hopefully.
Okay, so where do we start? How do we make these SPV deployments work well? What were some of the key high-level takeaways from that draft?
Well, one of the standout benefits, you consistently see this, is the incredibly rapid recovery after a network failure.
Okay, speed.
We're talking convergence times in milliseconds, well under a second.
Wow.
And the document really emphasizes that achieving this speed, it really hinges on using point-to-point connections between your SPB devices.
Direct links.
Think of it like a direct line. If there's a break, you know exactly where the problem is instantly.
Right.
It's a big contrast to older stuff like traditional spanning tree,
Yeah.
where a failure could trigger a much longer recalculation process.
Yeah, the whole network rethinks itself.
Exactly. So avoiding shared network segments is really crucial for that quick failover.
That makes intuitive sense. Direct connections means simpler fault finding, and it sounds like SPB uses specific tricks, specific mechanisms to detect these failures quickly.
Absolutely. Their recommendations strongly push for using built-in Ethernet fault detection tools, things like remote fault indication, RFI,
RFI, okay.
and the IEEE 802.1AG standard for connectivity fault management, or CFM. That's key.
CFM, yeah.
These protocols, they actively monitor the link health and can quickly flag a problem. That then lets the SPB control plane rapidly calculate a new optimal path for traffic.
So fast detection leads to fast healing.
Got it.
Now, SPB is also known for its network virtualization using these service IDs or ICE IDs. How does that practically simplify things?
Well, think of the ICE ID as a unique tag for a virtual network service, maybe a specific application or a particular tenant's traffic.
Like a label.
Exactly.
Right.
And SPB uses a 24-bit space for these ICE IDs.
Yeah.
That's way bigger than the old 12-bit VLAN ID space.
16 million versus 4,000 roughly.
Right, big difference. And the recommendation is to use endpoint-only provisioning.
Endpoint only.
Yeah. It means you can manage VLAN numbers locally within different parts of your network, like in each data center, without having to coordinate one single massive VLAN numbering scheme across the whole infrastructure.
Ah, okay.
It's like having a much larger pool of virtual network apartment numbers, and you only need to worry about unique numbering within your local building, so to speak.
Okay, so a much bigger set of labels, easier to manage locally. But how does this help with those really large distributed setups, like multiple data centers that might already have their own VLAN numbers?
Ah, that's where it really shines. The recommendation is to define a global virtualization strategy based on these ICIDs.
Global ICIDs.
Right. Instead of trying to force a one-to-one mapping between VLANs and ICIDs across the entire network.
Right.
This becomes incredibly useful when connecting multiple data centers, each maybe with its own legacy VLAN numbering.
Yeah, avoiding clashes.
Exactly. You map those local VLANs to unique global ICE IDs within the SPB fabric. It avoids conflicts and greatly simplifies connecting those data centers, especially during things like migrations or consolidations.
That sounds like a huge win for management in complex places.
Yeah.
Now, what about the traditional spanning tree protocol, the one we all know and sometimes well?
Love the 8.
Yeah, exactly. How does SPB play with it?
SPB offers a couple really significant advantages there. First, you can use SPB to create smaller, independent spanning tree domains,
Yeah.
maybe just within your access networks.
Contain the blast radius.
Precisely. So if a root bridge changes in one area, it doesn't necessarily ripple through the whole network.
Okay.
But even more compelling is the possibility of just eliminating spanning tree entirely if you deploy SPB all the way out to your access switches.
Get rid of it.
Yeah. Because SPB inherently presents loops by its design, you just don't need spanning tree as that safety net anymore. The recommendation in the draft is pretty clear. Replace spanning tree with SPB wherever it's practically feasible. You get a more stable, more efficient network.
The thought of ditching spanning tree issues is definitely tempting. But what about routing? Moving traffic between these different virtualized layer 2 services, these IISIDs. How does SPB handle layer 3?
Well, you could use external routers, sure, but the document highlights some real performance and operational benefits of letting the SPB nodes themselves do the routing.
Internal routing.
Yeah, it's similar to how traditional layer 3 switches route between VLANs and IP subnets.
Right, router on a stick, but integrated.
Kind of. The advantage in SPB is that the routing instance for a particular IIC can dynamically exist on any SPB node that needs to support that service.
So it follows the service.
Exactly. If you extend an IIC to a new part of the network, the routing for that service could pop up there too. It's a much more agile approach to routing in a virtualized L2 world.
Okay, so SPB can offer a more integrated L2 and L3 story. Now let's get into some of the maybe fiddlier bits, setting up the infrastructure. The draft talks quite a bit about IS system IDs and SPB nicknames. Why are these identifiers so important?
These are really foundational. They let the SPB network function correctly. An SPB network, as it stands, operates within a single ISIS routing protocol area.
One ISIS area.
Right. So every SPB-enabled device needs to have the same ISIS area ID. And then each needs unique identifiers specifically, the ISIS system ID and the SPB nickname.
Okay, unique per device.
Think of the system ID as the unique name of each device in the SPB network. And the nickname is a shorter ID used for some internal processes, particularly multicast traffic handling.
And what's the recommended way to set up this ISIS area ID? How do you define your SPB zone?
The recommendation is to use the format 49.xxx.
49 dot something.
Yeah. The 49 basically signals that it's a locally administered network service access point or NSAP address. Yeah. Private use, essentially. The XX part is then up to you. You define it to uniquely identify your specific SPB network. You might see common ones like 49.0000 or 49.0000.
Makes sense, setting up your own private routing world. Now, the system ID, the document says it's the same as the node's backbone MSC address, the BMAC. Why is it so vital that each one is absolutely unique across the whole SPB network?
Uniqueness here is absolutely non-negotiable. If you somehow end up with two SPB nodes having the same system ID, it causes chaos.
Right.
Big problems with routing, connectivity breaks down.
Yeah,
network chaos is a good description.
Okay, so how do we guarantee uniqueness? The draft mentioned 3 ways.
Yeah, 3 approaches. Option 1, let the SPB devices auto-generate their system IDs based on their built-in MACs.
Taking the hardware emphasis.
Right. That inherently ensures uniqueness because MACs are unique. But the downside is these IDs can be hard for humans to recognize. Troubleshooting gets tricky.
Yeah, trying to find switch A8.B1.DCOFFEE isn't fun. What's the second, more user-friendly way?
The second, and generally the recommended way, is for the network admin to manually provision unique system IDs. Admin assigned, following a well-defined scheme. The draft suggests a format like 02y.yyxx.xx0.
Okay, what do those parts mean?
The O2 at the start indicates it's locally administered, manually set. The yy.y bytes, you could use those to reflect maybe the node's physical location or its role core, distribution, etc. Makes it identifiable.
Embeds some meaning.
Exactly. Then the xx.xx ensures a unique number for that specific device within your domain. And setting the last byte to 00 is often just good practice for consistency.
That structured approach sounds much better for operations. What about the third option, a mix?
Yeah, the third is a hybrid, tries to balance manageability and automation.
Best of both?
Maybe. For your core and distribution switches fewer, more critical, you'd use those nice administrator provisioned IDs.
Okay.
But for the access layer switches, where you might have tons of devices.
Hundreds, maybe thousands.
Right. You could rely on the automatic generation from their factory MAC addresses.
Okay, but how do you avoid clashes?
Good point. You have to be careful. You need to make sure the range of IDs you manually provisioned for the core distribution never overlaps with the MXC address ranges used by your access switch vendor.
So you need to know the vendor OUIs.
Exactly. You need to understand their organizationally unique identifiers, the first part of their MXCs, and steer clear.
Okay. A strategic mix depending on the network layer. Now let's talk nicknames. The SPBM nickname. What's its job, and why does it also need to be unique?
The The nickname is shorter, just 5 nibbles, so 20 bits. Its main job is to help the SPB network efficiently build and manage multicast traffic flows for specific ISID services.
Multicast helper.
Yeah. And just like the system ID, it's absolutely critical that every SPB node in the network has a unique nickname. If nicknames collide, multicast traffic can get seriously disrupted.
Okay, same rule. Uniqueness is king. How do you make sure they're unique? Same options.
Pretty much. Similar to the system ID. One way is auto-generation. The devices pick their own. But the draft notes that vendors support for this might vary. Not all might do it or do it well.
Okay.
So the other way, often preferred, is administrator provisioning again.
Manual assignment.
And the recommendation is to tie your nickname allocation directly to how you allocated your system IDs.
Link them together.
Yeah. Makes sense, right? If you're using that 02yy.yyx.x00 format for system IDs, you might adopt a corresponding 01xx.xx format for the nicknames, maybe using the unique xx.xx part.
Okay.
If you're using auto-generated system IDs for access switches, maybe use a different nickname prefix like 1.0 for those.
Distinguish them.
And for the hybrid approach, you just combine those strategies, keep them consistent.
Got it.
Oh, and there's an important warning. Avoid using nicknames starting with 3.33.xx.
Why is that?
Potential conflict with MAL addresses used for IPv6 multicast. Just best to steer clear of that specific range.
Good practical tip to avoid headaches later. Let's shift focus now to how these SPB nodes actually connect, the links between them. What are the key recommendations there?
The consistent advice, based on those real deployments, is stick to dedicated point-to-point Ethernet links, or optical fiber connections, or transparent E-line services.
Dedicated links.
The crucial thing to avoid is running SPB over shared network segments, like old hubs or even shared L2 switches not doing SPB.
Why avoid shared?
Because shared segments can really complicate and slow down failure detection and convergence. Those things are central to SPB's advantages. You want that quick, clean detection and switch over if a link fails.
So direct dedicated paths are best. What about using those transparent E-line services like from a service provider? Any catches?
Yeah, they can work fine. Things like wavelength division multiplexing, WDM, MPLS-based VPLS, or even provider backbone bridging, PBB E-lines are generally suitable.
Okay.
But a couple of important conditions. First, the underlying transport network itself must be loop-free. SPB assumes that.
Makes sense.
Second, they need to support a minimum MTU, maximum transmission unit.
Big enough packets.
Right. The draft specifies a minimum of 1,544 bytes. That's to make sure there's enough room for the original Ethernet frame plus the extra SPB headers.
Okay, 1544 minimum.
And one more thing with provider links. Just watching the link status light on your end might not be enough. A failure could happen deep inside their network.
Right, the light's green, but the path is broken somewhere else.
Exactly. So using an end-to-end connectivity check like that IEE 802.1 AGCFM we mentioned earlier is highly recommended to actively monitor the entire path health.
Proactive monitoring. Basically, ensure the transport is solid, roomy, and verifiable end-to-end. Now, we touched on spanning tree before. The draft has a whole section on SPB and spanning tree. Remind us of the key recommendations for how they should interact or not interact.
Right. As we said, SPB can shrink spanning tree domains or even get rid of it. Now, it is technically possible to run traditional protocols like MSTP over an SPB region, maybe sharing a common spanning tree CST instance.
Possible.
But the recommendation is be cautious, especially if you also have non-SPB VLANs running over the same physical links that the SPB fabric uses.
Why is that risky?
Because a change in that shared CST topology, triggered by something maybe unrelated to SPB, could then unintentionally block or disrupt those non-SPB VLANs that happen to share the path.
Ah, unintended consequences.
Exactly. So the strongest recommendation is actually to just disable MSTP entirely on the in and out links, the network-to-network interfaces that form your SPB fabric.
Turn it off on the SPB links, yeah.
That prevents any spanning tree state changes from messing with your SPB services. Keep them separate.
Okay, generally best to keep the worlds apart on those interconnects. Let's talk more about the core SPB network itself, configuring the fabric. What are the crucial recommendations there?
Well, a key point is that SPB is designed to play nice with other IE standards.
Good neighbor policy.
Kind of. It means you can often introduce SPB into an existing IE-based network without a massive rip and replace, provided you avoid overlap between the backbone VLAN IDs, the BVDs SPB uses, and your existing traditional VLAN IDs.
Okay, BVDs. What are they for?
They're used internally by SPB to separate and, importantly, load spread SPB traffic. The standard defines up to 16 BVDs you can use.
16 internal VLANs for SPB.
Sort of, yeah.
Yeah.
And it's essential you configure these BVDs consistently across all the SPB devices in your network region. Everyone needs the same set.
Consistency is key. And how do you choose them?
The recommendation is pick them from the higher end of the VLAN ID range, like start from 40, 51 or somewhere up there.
Why high?
Because the lower ranges, 1 through 1,000 or whatever, are often already heavily used for user access VLANs. You want to avoid clashes.
Right, stay out of the busy area.
And crucially, it's also recommended to use at least 2 BVDs within your SPB fabric.
Why 2 or more?
For load spreading, it lets the SPB fabric distribute traffic across different internal paths, improving overall performance and resilience.
Spreading the load using multiple BVDs makes sense, good for bandwidth, and if one path has issues. Now let's circle back to those service IDs, the ISIDs. The draft spent a lot of time on mapping services to these. What are the best practices for ISID allocation?
Right. With that huge 24-bit space, over 16 million IDs, the most critical recommendation is develop a clear, logical allocation scheme.
Plan it out. Don't just pick random numbers.
Exactly. While you might have descriptive names on your switches or management system, embedding structure within the ISID value itself can really help you quickly recognize the service type just by looking at the number.
Like a code within the ID.
Precisely. The suggested format is YSXXX, where Y is 0 to 15 and XX is 0 up to 999,999.
Okay, YSXX.
This lets you encode meaning right into the ID.
So you're basically putting hints about the service into the number itself. Are there any ISID values we should definitely not use?
Yes, definitely. There are several reserved by IE for specific standard functions.
Don't touch these.
Right. These include 01, the range 2 through 254, then 255, and the very top value, 16,777,215. Avoid using those for your services.
Okay, standard reservations. Anything else?
Yeah, also be aware that many vendors reserve certain ISID ranges, usually up above 16 million, for their own proprietary or advanced features.
Vendor-specific stuff.
So always check your vendor's documentation. See if they have ranges you should steer clear of as well.
Good advice, like avoiding reserved keywords in code. What's the big payoff for having a really well-planned ISID allocation strategy?
Well, think of the ISID in SPB as being kind of like an inner label in MPLS.
The service identifier.
Exactly. It's the key that lets SPB deliver all sorts of services, point-to-point E-lines, multi-point E-LANs, E-tree services, even IP VPNs.
Versatile.
Very. And a logical ISID scheme helps you instantly know what kind of service an ID represents. For example, using that YI part in ISXX, maybe O1 is always E-line, O2 is E-lane tree, O3 is IP VPN, and so on.
Makes troubleshooting easier.
Definitely. You could even embed an administrative domain identifier in there, maybe like YA8XX.
Ah, like department or tenant.
Could be. Now, here's a crucial point for performance. Allocate ISIDs sequentially within the same service type and administrative domain.
Sequentially. Why?
Because SPB often uses simple load balancing math, like even, not, or round robin based on the ISID number, to spread traffic across those BDDs we talked about.
Ah, the load spreading.
Right. If you allocate ISIDs non-sequentially, like service 1 ends in 10, service 2 ends in 20, service 3 ends in 30, you might accidentally funnel all that traffic down the same BVD path, leaving others idle.
Okay, so sequential numbering helps the built-in load balancing work properly.
Exactly. Keeps the traffic spread out nicely.
So a systematic ISID plan is key for organization and getting the best performance. Now, how does SPB mesh with good old IP routing? Do you still need routers?
Oh, yeah. In an SPB network, the size of your broadcast domains for user and server subnets, that's typically similar to traditional networks.
No magic bullet for broadcast storm.
Nope. So you'll still need IPv4 and IPv6 routing, usually sitting on your core and aggregation SPB nodes.
The bigger switches.
Right. Those larger SPB-enabled devices, often called Ethernet routing switches, they can directly route IP subnets that are mapped to specific ISIs. It's very much like how they route between VLAN-based subnets today.
Okay.
So the common enterprise model, routing at aggregation, bridging at access, that generally stays the same with SPB.
Same basic architecture.
Pretty much.
Oh.
However, in data centers, there's a strong push to combine bridging and routing right at the first hop, top of rack switch, for instance.
Closer to the servers.
Yeah. That gives you lower latency, better bandwidth use, more efficient traffic flow. Especially good for things like VM migration using L2 extension, while still getting L3 shortest path forwarding for other traffic.
Best of both worlds at the edge.
Exactly. And for IP routing redundancy, especially in access networks connecting to the SPB core, the recommendation is just stick with what works. Use VRRP or similar protocols on your core aggregation SPB nodes.
Standard router redundancy.
Yep, no need to reinvent the wheel there.
So SPB beefs up L2 but doesn't eliminate the need for a solid L3 routing design. Now, the draft also had a section on OA&M operations, admin, and maintenance. What's critical for managing an SPB network effectively?
Layer 2 OA&M tools are presented as absolutely essential. You really need them for managing and troubleshooting SPB.
Can't fly blind.
Definitely not. The document strongly recommends deploying IEE 10 802.1ng based Maintenance Association endpoints, MEPs.
802.1 AJ again.
Yeah, with a minimum maintenance domain level of 4.
Level 4.
That's the baseline. Now, if your SPB network stretches across Ethernet services from a carrier, you might need to bump that up to level 5.
Why higher for carrier services?
To avoid potential interference or clashes with the provider's own OAM domains, which might be operating at lower levels.
Wow.
Keeps your diagnostic separate.
Okay, stay out of their way. What specific tools does it mention?
The 802.1ng CFM mechanisms, Layer 2 ping, Layer 2 trace route, and also something called trace tree, are highlighted as invaluable for debugging network issues within the SPV fabric itself.
L2 troubleshooting tools are key, so standard Ethernet diagnostics are vital for SPB health. The draft then shared some real-world deployment stories. Can you give us a quick flavor of one or two? Show us SPB in action.
Sure. One interesting one was using SPB for Data Center Interconnect, DCI.
Linking data centers.
Right. Imagine you got two DCs, geographically separate, and you need to stretch server VLANs between them. For redundancy, maybe for VM mobility.
Common requirement.
Very. SPB, paired with ISES, makes this easier. You can keep your local VLAN numbering in each DC, but then map them to unique global ISIDs in the SPB fabric that connects the two sites.
Local VLANs, global ISIS.
Exactly. Standard IP routing, VRRP handle the L3 side and redundancy. The draft even mentions the plus of having distributed virtual routing right down at the top of rack switch level in these setups.
Pushing routing closer to the servers again. Okay, another example.
Another cool one was re-architecting network security zones.
Security zones? How?
Instead of security being strictly tied to where a firewall physically sits, SPB lets you decouple the physical gear from the logical connectivity.
Abstracting the connections.
Yeah. It means you can have a Layer 2 VLAN reach a specific firewall service, regardless of where that firewall physically plugs into the network. It gives you way more flexibility in segmenting and securing different network zones.
That sounds powerful. Like you can route traffic to security services logically, not just physically.
Exactly. Much more flexible design.
Those examples really do bring it home how SPB can tackle real-world networking problems, from DC resilience to flexible security. The draft also mentioned security and IMANA things briefly. Anything major there?
Not really the focus of this document. It just notes that SPB security implications are covered in other specs.
Okay.
And it confirms there were no requests made to IANA, the Internet Assigned Numbers Authority, in this particular draft. Standard stuff. But it does provide a useful list of references, the main 802.1AQ standard, related RFCs, even a link to the SPB DB AKI, which was like a community hub for interop testing info back then. And it lists the author's context too.
Okay, standard draft appendices. Right, we've covered a lot of ground, from the basics of SPB deployment, the why, to detailed config tips for IDs and links, and even some real-world use cases. To wrap it all up, what's the single most important takeaway from this deep dive into these SPB deployment recommendations?
I think the overarching message is that SPB really offers a robust, adaptable framework for tackling a lot of modern network challenges.
It's a solid toolkit.
Yeah. It strengthens things like fast convergence, efficient virtualization with ISEs, supporting multi-tenancy.
Yeah.
These aren't just theory. They're proven benefits backed by real-world success stories, like the ones in this draft.
And for our listener, the learner who's taken all this in, what's the core value? Why should they care about this deep dive into an old draft about SPB?
Well, this deep dive has hopefully given you a condensed but still pretty thorough understanding of the critical factors for actually deploying SPB successfully.
The practical stuff.
Exactly. By focusing on the advice pulled from real implementations, you've gained insights into best practices, potential applications. It gives you a real head start if you're evaluating or discussing SPB technology.
So it's a shortcut to understanding the real-world wrinkles of SPB deployment. And that brings us to our final thought for you. Given SPB's demonstrated success in these very demanding places, the Olympics, multi-tenant DCs, it makes you wonder, What other networking paradigms, maybe even established ones, could benefit from adopting similar ideas? Ideas like abstracted logical connectivity, dynamic path calculation. Think about how those concepts might drive the future of network agility and how we optimize network resources going forward. Something to chew on. Thanks for taking this deep dive with us.